So I'm going to talk about a mission concept. So I feel a little bit like I'm much more narrow than the talks this morning, so I apologize for that. But I think this mission does qualify in terms of it's a kind of a high-risk thing. So if we put it on the stock market, I think it's probably not going to be a gilt-edged or a blue-chip bond for sure. I'd like to think I'm somewhere in the, the S&P 500 high-risk, high-return kind of zone. And you can judge for yourself whether I'm a junk bond at the end of the talk. Here's an overview of what I'll be talking about. So as Olivier said, I spend a lot of my time throwing away photons, so I think I need a little bit of a historical introduction and to try and convince you that that's not the world's craziest idea. I'm also going to talk about astrometry and diffractive pupil astrometry in particular. And then at the end of the talk, I'll come to my mission concept. So to start with a little bit of history, and here's the audience participation part of the talk. We probably have a lot of technical people in the audience and people who've done interferometry. Who knows what the very first quantitative measurement performed by interferometry was? What was it of? What were they measuring? Betelgeuse? Michelson-Morley? Sorry? Way before this. So the first measurement of any quantity with interferometry. So in fact, it was Thomas Young, who is, I think, underrated as one of the world's great geniuses. And it was a fact of blood and pus. And you can find this. This is the original paper. And he compares mouse blood with human blood. He, in fact, got the first measurement of human red blood cells, which is pretty cool. So following his generation, there was an explosion of interest in this. And it's interesting that stellar interferometry was one of the first things they thought of doing. So it was only, it's now 150 years old. It'll be 150 exactly next year, the first measurement of a star by interferometry. That was performed by Stéphane with this telescope in Marseille, and he used an aperture mask, just a plate with two holes in it that let the light through. And that was, of course, continued, as you probably know, by Michelson, famously at Mount Wilson. So what I do is exactly this. I take a big plate and I stick it over a telescope and I chuck away lots of photons. So I'm using 150-year-old technology, and I guess I just put this up here as a visual metaphor for what I'm doing. I'm flying one of these at the bottom right here in an era when everybody else has got laser guide stars and AO systems and very, very complicated technologies. So how does that work? How do you even let me on the telescope? Well, in actual fact, it turns out that this is not the world's stupidest idea, and it is still has a niche. And my own career has really been very much centered around this technology. There are now masks on every 8-meter telescope in the world, and almost every instrument on every 8-meter telescope that does high-resolution imaging. There's sort of 25 of them or 30 of them. I've pretty much designed most of them at this point, although some of my postdocs are now out on their own. And this is just an example of a recent spectacular result. So masking kind of owns this piece of parameter space that's very, very close to the diffraction-limited core. If you want one lambda on D planets, then you probably want to come to me. This is a lovely image of the calcium-15 planet, which has been proven to be accreting, active accretion from H-alpha there. And if that wasn't enough, we've also got an aperture mask on the James Webb Space Telescope, and you can ask me later how a technology that's based on overcoming atmospheric turbulence can go on a space telescope, and I could talk about that. So what I'm proposing here is something quite distinct from my previous aperture masking days. I'm talking about an astrometric mission to Alpha Centauri. So everybody else hates this binary because it mucks up their attempts to do good, make a coronagraph to get rid of the light. But in fact, Alpha Centauri just turns out to be absolutely perfect, and it's really kind of fluky how perfect it is. So narrow angle astrometry, almost all astrometry, the errors you get are proportionate to the angles you're trying to measure. So if your reference star is 10 degrees away, that's twice as bad as a reference star that's only 5 degrees away. Most of the errors run in that kind of sense. So Alpha Cen happens to have this reference star just right there, 5 arcseconds away. So that's a big tick. And you would think that's great, except that the challenge is still pretty severe. The motions you get, the gravitational perturbation from the companions, from planetary companions, is only of order hundreds of microarcseconds for Jupiter. We know there's not a Jupiter there. And it's only of order 1 microarcsecond for an Earth. So that's very, very hard. And it's beyond the sensitivity of any present mission. So Gaia will, of course, see a lot of these kind of gas giants by their reflex motions, but Gaia won't see any Earths. It won't see anything as low mass as that. So here's a kind of a list of why we have such a lucky break with Alpha Cen. It's a solar analog star. It's got 2 habitable zones around 2 planets. It's probably close to the sun. We'll come to that. Wide angle, so it's just perfect for my mission because it's wide enough for a small telescope to split the pair, but it's narrow enough that you can get them both in a close field of view and get this gain because the astrometric errors scale over only 5 arcseconds. That's a very, very small, you've got a very, very good reference very close by. Habitable zone planets have year-long orbits, so you only need to run your mission for a year. That's great. But you are still faced with a severe challenge. You need to get parts in 10 to the 7. If your reference is 5 arcseconds away and you need a microarcsecond, that's a part in 5 parts in 10 to the 7. So that's a very, very hard challenge still. So here is an answer to some of the questions that were asked previously. The plot on the upper left shows all of the near solar neighborhood stars with their locus, separation locus with time. So you can see now is at 0 here, so Alpha Cen in 30,000 years or something will be at its closest approach. The interesting thing about this plot, I think, is that there's Alpha Cen sitting there at the closest approach at the moment, and you don't recognize a single one of the others. There's Wolf something or other and Gliese something or other. There's all these random red dim objects that nobody cares about, and then we've got Alpha Cen sitting there as the one that's closest. It's amazing. Somebody set this up. On the right, you'll see the orbit as it sits in space is the big circle, and as it is apparently projected to us is the kind of elliptical one. Again, you can see at 2015, it's just at closest approach right now. That's great for me. I love that. That really helps my mission. On the lower left, the lower right, the lower left, you can see the perturbations that will be imposed by a Jupiter mass planet on the sun. That's just an illustration of the way the detection scheme we want to try and implement here works. So we measure the separation of the binary, and we look for a planet that's tugging it around. But it's a very small tug. You can see for Jupiter, we get of order 1,000 microarcseconds, 700 microarcseconds. We know there's not one of them there, but we're looking for 2.4 microarcseconds for an Earth around planet A and 1.2 microarcseconds for B. It's interesting that B is smaller than A. You might think a planet would tug a lighter star around more, but it goes the other way. The habitable zone is closer in for planet B, component B, and astrometric signals are smaller the closer in you are to your host star. It's the opposite of RV. So what is this technology we're going to try and use to get this incredible measurement precision on the position of, on the separation of these two stars? So we're using a thing called a diffractive pupil telescope. And this is an image from my masking campaign that just shows you get, all optical systems will produce a distorted image. And what you want to do is make measurements of those images. So what would be really cool is if your ruler got distorted in the same way as your signal. So this is, the solution is to make your ruler out of the starlight that's coming into the telescope. Then it undergoes all of an identical set of perturbations and distortions and errors. So this is called a diffractive pupil approach, and you use the diffraction pattern itself as the ruler. So there are errors that are completely eliminated by this. This is the good part in the top. You don't care anymore about changes in the telescope focal length because that is common mode between the diffraction pattern and the thing you're measuring. So all common mode changes, changing the pixel scale if it expands or contracts. All of these things are common mode and are not part of your measurement process. There are a couple of things there that do matter. If your wavelength changes, that'll change the diffraction pattern, but not the separation of the binary. And if the physical size of the mask changes, that'll also be a problem. But as it's presently formulated, what you normally do is you just have this pattern of dots on your primary mirror, illustrated in the red box there. And it's very good for bright stars, and those diffraction rays extend out, and all the faint stars around it can then be used as references. That also helps with your contrast problem, because it's hard to get the bright star and the faint surrounding stars all on the same chip. Instead of that, what I'm doing here is I've kind of reformulated diffractive pupil idea into an aperture mask concept, which turns out to work beautifully for the case of close binaries. So I've got this weird-looking pupil here, all these eggs around the edge. So basically, you paint the mirror black except for those regions. And what that does is it spreads the light out over this larger sort of funny pattern you see there. So the elliptical holes are formed because if you imagine they were circular holes, then the primary beam would carve a large primary dark ring in your diffraction pattern. That would be a blind spot to you. So if you have this diversity of ellipses, there are no large features in the, there's just, what you want is a carpet of fringes going everywhere so you can measure things with. So there's a bunch of thinking has gone into this, but nothing really carefully optimized. And this is the way it would work in practice. You would just look at alpha sen and you get an image a bit like the one on the right here. It's not showing up so well at the contrast I'm getting on the projector, but I'll show you another one later. So we can start putting numbers into this. We can probably get a 10% fractional bandwidth, and we can start trying to design a skeleton mission around this idea. We spread the light out so that the diffraction covers the area between the stars, giving us a ruler in between. What sort of precision do we think we're going to get? Well, if photon noise is the only problem, and we chuck in some sort of Straw.man ideas for how the telescope should look, we get about 0.4 microarc seconds per hour on alpha sen, and we get 1.4 microarc seconds per hour on a fourth magnitude binary star of equivalent separation to alpha sen. This is a nice number to have. If we could do that, that would be great. Of course, I haven't spent a month or several months looking at all the systematic sources of error. If you ask the question, how much would temperature of the one error source that's systematic that's easy to calculate is the temperature of the primary mirror. And if you calculate that, you only need something like 1 degree or so stability, and you can trade knowledge for stability. You can just back that out of your data if you know what the temperature is. So it's not such a demanding requirement. One thing is everybody always complains about masks because they waste light. In actual fact, you can get more light. You can record more photons with a masked aperture than with a filled aperture. And that's because if you use a filled aperture to observe alpha sen, you'll saturate your detector on anything larger than about a 10 centimeter telescope. There's so many photons coming at you. So you've got to spread the light out somewhere. That's what Kepler does. It defocuses to spread that light out so it's over many pixels. What I do is I use the mask, and that does that naturally and also gives us our measurement technology. So I've called this thing TOLIMAN, which is actually one of the ancient names for the alpha sen system. And there's some Straw.man ideas about data rates and things. It all looks kind of manageable. A 30 centimeter telescope could do this. Just to remind you though, we're doing something really crazy here. We're doing something like 1/1,000,000th of the diffraction limit is the number I'm claiming I'm able to produce to you here. So it's, you know, you can kind of cut me apart in question time for trying to do that. It's also about 1/1,000,000th of a pixel. So it's a very, very hard problem. But one of the nice things about it is this pattern we get. There's the binary in a sort of a stretch that you can probably see. This pattern we get distributes the information over the whole chip. So you're not just trying to find 5 pixels here and 5 pixels here and measure the size between them. The information, it's kind of like a hologram. You could actually chop the middle part out, just use the outer part of the pattern, and you would still have all the information in principle. You wouldn't have the same signal to noise, but any piece of that pattern, you should be able to fit both binaries to. So just the last slide before I click back to my thank you slide. One thing we probably want to do is monitor a bunch of other objects because that also gives us metrology of our mission, how things are going in case something's drifting. There are a bunch of stars here. This is the distance column. Sorry, on the right is the distance. And the distance tells you, so there's a couple of nice binaries. These are all bright binaries that would be potential candidates for secondary science and also to calibrate the mission as we go. So there's several at 5 and 10 AU that look quite promising as well. And there's some brighter ones further away that would simply be used for mission calibration. So I've run a minute over time, and thank you for your attention.
We have time for a couple of questions. Jeff, there's a microphone. Oh, okay.
Peter, what happens if there's a slow drift in the collimation between the primary and secondary? Does that come out of the analysis?
I think all simple optical aberrations like that should be common. Well, firstly, you would be able to tell because you're recording your data. I mean, at the level of 1/1,000,000th of a pixel, everything like that is happening all the time. Nothing is stable at that level. If you make, for example, if you make something out of we're looking at simpler materials than composites or things like fiberglass or, carbon fiber. Those things, at the level of 1 parts in a million, they're always moving. They never actually stop. You make them and they cure, and then they keep curing forever at that level. So yeah, it's a good question.
Very intriguing, Peter. Cool question. This looks like it's a narrowband image. Is that right?
Good question. Yes, it isn't. This is a monochromatic image. So if you did this in reality, and I have got other images where I've simulated this, you would see the diffraction pattern still looking sharp around the middle, and then you would get bandwidth smearing further out in the pattern. So the pattern would become less and less useful with radius. So there's a trade-off there. If you make a very, very narrow band filter for the mission, you get less photons in, but you get a larger piece of the pattern that has high contrast fringes to grab onto. Essentially, your data output, what you do is you take the image you see on the screen and you just fit two PSFs to it, and that's your outcome. That gives you the binary separation. But yeah, as you go to broader bands, so there's a trade there. As you go to broader bands, it's harder to fit.
So what band are you thinking of for the mission?
The bandwidth is convolved with also another factor that comes into it is the size of the holes. The smaller you make the holes, the larger the pattern is, and that forces you to narrower bandwidths. And then so there's some trade here between photon noise, and the Straw.man version of it we have at the moment has a 10% fractional bandwidth and holes of about 6 centimeters on the primary. But you can kind of see you're grabbing onto all of this high detailed structure. It's very easy to centroid because you're centroiding on 1,000 speckles all around the cloud. It's a very, very, imagine fitting to that. You can only fit it in one place. It's a really, the high contrast structure gives you a very good thing to grab onto.
We'll take one last question.
I'm Jerry Hart, SETI Institute, and you're a good demonstration here of a peeve that I have about astronomers, that they never put scales on their pictures. So what is the dynamic range in that image?
Oh, so this is a pretty image that's not particularly scientifically valid. It's clearly saturated in the core. So approximately 80% of the light is in the diffraction halo, and about 20% of the light falls in the core with this particular mask. So you can make other masks that have a different ratio. This is a logarithmic stretch with a weird color table. So clearly, things are very, very much brighter in the middle than the outside. On a linear scale, all you would see is a tiny dot in the middle. But yeah, 80% of the light is in the outer pattern, and that's what you're trying to grab onto. Well, the core is also equally useful. Every photon has more or less the same value when you're trying to centroid.